Hi everyone. In the last two classes, we have discussed about positive operators, self-adjoint operators, and normal operators. In the today's class, we are going to discuss about isometries and unitary operators. Let us first define what is an isometry and what is a unitary. Then we can discuss some properties of these operators. Let T be a bounded operator on H, then T is said to be an isometry if norm Tx equal to norm x for every x in H. It is said to be a unitary if T star T equal to T star, that is identity on the Hilbert space H. So let us quickly look at examples. So let us look at the right shift operator on L2. R of x1, x2, x3, so on, by defined by 0, x1, x2, x3, so on for every xn in L2. Now we know that R star of x1, x2, x3, so on, this is nothing but x2, x3, x4, so on for every xn in L2. So this is the left shift operator. Also, if we compute norm of R of x, so let us take x as x1, x2, x3, so on. Then we can look at norm of Rx with respect to the L2 norm, that is norm of 0, x1, x2, x3, so on, and this is exactly norm of x. So we can say that R is an isometry. Also, we can easily to verify R star R is an identity operator, but R star E1, if you look at, E1 is the first element in the standard orthogonal basis of L2. We know that R star of E1 goes to 0, so this is 0. So hence we can say that R star is not equal to the identity. So the conclusion is that R is an isometry, but not unitary. Okay, so let us slightly generalize this example to a more general setting. Let us start with a separable Hilbert space. Let H be a separable Hilbert space with an orthonormal basis phi1, phi2, phi3, so on. So define T from H into H by T of X equal to summation n equal to 1 to infinity inner product X with phi n multiplied by phi n plus 1 for every X in H. This is exactly the generalization of the right shift operator that we have defined on L2. So we can easily check that, we can easily verify that norm of x square is exactly n equal to 1 to infinity inner product X with phi n mod square. So this is exactly norm x square for every X in H. So hence we can conclude that T is an isometry. Here we can easily show that T star of X is nothing but summation n equal to 2 to infinity inner product X phi n multiplied by phi n minus 1 for every X in H. And also we can easily show that T star T is identity, but T star is not identity, as T star, if you take T star phi 1, that is 0, hence this part is 0. So this is an isometry but not unitary. So the conclusion is the following: T is an isometry but not a unitary. Okay, if you look at these two examples, we can conclude that both of them are not onto. Both R and T defined above are not onto, because in the first case E1 has no pre-image, in the second case phi 1 has no pre-image. So this is the observation. So let us look at one example of unitary operator. So define U from L2 of Z into L2 of Z by U of En is En plus 1 for every n in N. So here En is the standard orthogonal basis for L2 Z, where n is ranging over integers. So here En at M is delta Nm for all m in Mn in Z. Okay, we have already seen that in this case U star of En is En minus 1 for all n in Z. We can verify that U star U En is En, and that is equal to U star En for every n in Z. Not only that, we can even verify that U star Ux is X, that equal to U star X for every X, for every X in L2Z. That means, so we can conclude that U is a unitary operator. Here if we observe we can say that U is onto. U is isometry and onto. And in fact, U star is also isometry and onto. But if you look at the earlier example, the right shift operator on L2, so R is an isometry, but its star, R star, is not an isometry. And we have already observed that R is not onto. So from these two observations and with these two examples, so we can get an idea that there is a lack of surjectivity in an isometry, which makes that as isometry but not unitary. Now the question we can ask is that what are all the characterization of unitary operators? In other words, we can say that when an isometry is a unitary operator. So before addressing this question, first we want to characterize isometries, then we can discuss about characterization of unitary operators. Theorem. Let T be a bounded operator on H, then the following are equivalent. T is an isometry. This is equivalent to that T star T. This is equivalent to inner product Tx with Y is nothing but inner product Tx with Ty is inner product X with Y for every xy in H. The third one is T star T is an identity operator. Let us try to see the first condition, that is nothing but norm Tx equal to norm X for every x in H. That means T preserves the distance. So, and the second condition says that T preserves the angle between x and y. So preserving inner product is nothing but preserving the angle. And the third condition is a condition which is expressed in terms of adjoint. Earlier we have defined self-adjoint operators, normal operators in terms of adjoint only. So, but when it comes to isometry, we have defined in terms of the distance, but that is also equivalent to the fact that T star T is identity. That means we can define isometry in terms of adjoint of the operator. Proof. So, suppose T is an isometry. Let us try to prove 1 implies 2. So, if norm Tx equal to norm X for every x in H, then we have norm Tx inner product Tx with Tx is inner product x with x for every x in H. So we are squaring both sides. From that we can conclude that inner product Tx with itself equal to inner product x with itself. Now to conclude the result, we have to apply the polarization identity. So by the polarization identity, you can get inner product Tx with Ty is inner product x with y for every xy in H. We have already discussed the polarization identity in the earlier discussion. So here we have to say that this is T star T inner product x with x is inner product x with x for every x in H. Now T star T is a self-adjoint operator. Now apply the polarization identity that we have already seen. So from this we can conclude that T preserves the inner products. Now let us look at 2 implies 3. If Tx inner product with Ty is exactly inner product x with y for every xy in H, so this implies T star T inner product x with y equal to inner product x with y for every xy in H. Now from this we can say that I minus T star T at x inner product with y is 0 for every x and for every y in H. Now from this we can say that T star T is identity. This is the proof for 2 implies 3. Now 3 implies 1. T star T is identity implies inner product T star T x with x is inner product x with x for every x in H. This implies that norm Tx square equal to norm x square. So that again implies that norm Tx equal to norm x for every x in H. So from this we can conclude that T is an isometry. Okay, so these are equivalent conditions for a boundary linear operator to be an isometry. Let us look at some more important observations. Now let us start with a orthonormal set in H. So for the time being, let us assume that H is separable. H is separable. We know that every Hilbert space has an orthonormal basis. When H is separable, it has a countable orthonormal basis. Otherwise, it can have uncountable orthonormal basis. So let us take an orthonormal set phi 1, phi 2, phi 3 be an orthonormal set in H. Now if T is an isometry, we know that it preserves the distance as well as the angle between two vectors. Now that if you look at norm T phi n, that has to be norm phi n, that means that is 1. And if you look at inner product T phi n with T phi m, that should be inner product phi n with phi m. So we can say that T of this set, image of this set under T is also an orthonormal set in H. So then we can say if T is an isometry, then T phi 1, T phi 2, T phi 3, so on. This is an orthonormal set for H in H. Now the question is, if we have an orthonormal basis, can we say that the image of an orthonormal basis under an isometry is again an orthonormal basis? So in fact that is not true. So let us take, this is the question, if T is an isometry, is it true that I am repeating, let T be an isometry. Is it true that T maps an orthonormal basis of H into an orthonormal basis of H? ONB of H. So we can give an example. This is not true. So consider the redshift operator on L2. So here n is the standard orthonormal basis all the time. We know that E1, E2, so on is an orthonormal basis for L2. But if you look at RE1, RE2, RE3, so on, this is nothing but E2, E3, E4, so on. This is not an orthonormal basis for L2 because the first vector is missing. But what is the best result we can achieve is that, so we can say that if T is an isometry and then it sends an orthonormal basis of the domain into orthonormal basis of the range of the operator. So in fact this is if and only if condition. Theorem. Let H be a separable Hilbert space with an orthonormal basis phi1, phi2, phi3, so on, and T be a bounded operator on H. Then the following are equivalent. And the first one is T is an isometry. Second one is T of En is an orthonormal basis for range of the operator. So here we can say that the range of the operator is closed because whenever it is an isometry, so let me write remark. If A is an isometry, then A is bounded below. So that means range of A is closed and A is 1 to 1. So this is equivalent to the fact that range of A is closed A is 1 to 1. Okay. So let us look at the proof of the theorem. Assume that T is an isometry. 1 implies 2. Assume that T is an isometry. So we already have shown that whenever phi n is an orthonormal set, T of phi n is an orthonormal set in the codomain. So here also, so we have already shown is an orthonormal set in RT. Next thing we want to show is that it's an orthonormal basis. So let us take X in H. So since phi n forms an orthonormal basis for H, we can write x can be written as summation inner product x phi n with phi n. Then so from this we can say that hence T of x is summation n equal to 1 to infinity inner product Tx, this inner product x with phi n multiplied by T of phi n. Now since T is an isometry, we can say that the inner product can be written as inner product of x with phi n is nothing but inner product Tx with T phi n. So we are representing Tx with respect to this orthonormal set T phi n. Hence we can conclude that every element of the range is represented in this way. Hence we can conclude that therefore T phi n is an orthonormal basis for range of the operator T. We have already seen in the review of Hilbert spaces case that if an orthonormal set satisfies this condition, then we can conclude that it is an orthonormal basis, because this is a Fourier series of a given element in the space. Okay, so from this we can conclude that T phi n forms an orthonormal basis for range of T. So let us look at the other proof. 2 implies 1. So assume that T phi n is an orthonormal basis for range of the operator. We want to show that T is an isometry. So let us take x in H. Then we have x is summation n equal to 1 to infinity inner product x with phi n multiplied by phi n for every. Okay, so let us say this is equation 1. So this is a Fourier series representation for any element in a Hilbert space with respect to an orthonormal basis. So from this we can conclude that summation n equal to 1 to infinity inner product x with phi n multiplied by T phi n. So let us say this is 2. Now we know that T phi n is an orthonormal basis for range of T, and Tx is an element of range of T. So we can, so as T phi n is an ONB, we can say that Tx can be written as summation n equal to 1 to infinity inner product Tx T phi n multiplied by T phi n. This is for every x in H. This is nothing but, this is because Fourier series of Tx with respect to the orthonormal basis T phi n. So this is summation n equal to 1 to infinity inner product T star T x with phi n multiplied by T phi n, and let us call this as equation 3. But if we compare 2 and 3, we can say that summation n equal to 1 to infinity inner product T star T x minus x phi n with T phi n is 0. From this we can conclude that inner product T star Tx minus x, inner product with phi n is 0 for every n in n, because T phi n is an orthonormal basis for range of T. So this implies T star Tx equal to x for every x in H. That is, T is an isometry. From the earlier characterization. Okay, so this is one more characterization of an isometry in terms of orthonormal set. Okay, so we can easily show the following. Show that if ST are isometries, then we can say that ST is also an isometry. We can also discuss isometries defined between two different Hilbert spaces as follows. Let T be a bounded operator from H1 into H2. Then T is said to be an isometry if norm Tx in the second Hilbert space equal to norm x for every x in H1. So in this case we can show that T is an isometry if and only if T star T is identity on the Hilbert space H1, and that is if and only if inner product Tx with Ty is inner product x with y for every xy in H1. This is inner product in the second Hilbert space. This is inner product in the first Hilbert space. Okay, so next we want to discuss about unitary operators. We have already given one example of unitary operator, which is the bilateral shift operator on L2Z. Now we want to characterize unitary operators. So recall U in B of H is unitary if U star U equal to U star equal to identity. Now we know that when U star U is identity, we know that U is an isometry. When U star is identity, that means U star is also isometry. So we can say that U is unitary. So U is unitary if and only if U and U star are isometries. And we can also say that in terms of orthonormal basis, when T is an isometry, it sends orthonormal base of H into orthonormal base of range of T. But here when you look at the condition U star is identity, from that we can say that U is onto. So in this case U is unitary if and only if U maps an orthonormal basis of H onto an orthonormal basis of H, because it is onto. So these are the two important characterizations. In fact, from the definition we can actually obtain many important characterization of unitary operators. The proofs are similar to the earlier characterization of isometries. So we list out all the characterization of unitary operators. So let us take U to be a bounded linear operator on H, then the following are equivalent. U is unitary. The second one is, if U star U equal to U star is identity, U you can write as U double star. So from that we can conclude that U star is also unitary. And we have already observed that both U and U star are isometries. And this implies U is an isometry and onto, because when U star is isometry, kernel of U star is 0, that is equivalent to range of U, because range of U is closed because it is an isometry. So from that we can conclude that U is an isometry and onto. This is U is an isometry and U star is injective, that means null space of U is 0. And sixth one is U star is also an isometry and onto, equivalent to, we can say that U is bijective and U star is nothing but U inverse. When U star is an isometry, then U star is 1 1. When U star is onto, so range of U star is nothing but H, that is null space of U perp. So then U is 1 1 you will get. So we can actually you can show that U star is isometry plus onto implies that U star is bijection. From that U is bijection, and we can, by the condition that U star is identity, we can get U star is U inverse. Eighth condition is U maps an orthonormal basis of H onto an orthonormal basis of H. This we can get from the characterization of isometries, because unitary is nothing but isometry plus onto, and isometry maps orthonormal basis into an orthonormal basis of range of T, because it is onto here. So we can conclude that U maps orthonormal basis of H onto an orthonormal basis of H. So here again U is an isometry and normal. If U is isometry, then U star U is identity. If U is normal, then U star equal to U star U. So automatically it becomes unitary. 10th equivalent condition is U star is also isometry and normal. So these are the equivalent condition for an operator to be unitary. And most of the things can be proved by the earlier characterization of isometries. And for example, one equivalence of 1 and 2 and equivalence of 2 and 3 are directly follows from the definition, and 3 and 4 also directly follows from the definition. And for example, 9 and 10 are equivalent. 8 and 9 we can show easily from the characterization of isometry, and the remaining also can be shown in a easy way by sometime we have to use the inverse mapping theorem to conclude that 6 implies 7. So this can be proved in a easy way directly from the definition of unitary and the equivalent conditions of the isometries that we have already proved. Okay, so these are some important characterization of unitary operators. So the conclusion here is that U is unitary if and only if both U and U star isometries, that is very important, and an isometry plus onto automatically gives unitary. So that is the difference between unitaries and isometries. Okay, so here also we have the remark. If U is a bounded operator from H1 into H2, then U is said to be unitary if U is an isometry and onto. We can define unitary map between two different Hilbert spaces in this way. So in this case, U star U is identity on H1 and U star U is identity on H2. So in this case, we cannot say that a unitary map is or unitary operator is normal, but in the earlier definition, if you follow, then we can say that every unitary map is normal. Okay, sometimes we use this definition also, in particular when we prove the spectral theorem for normal operators, the multiplication form of the spectral theorem, we use unitary in this way. Okay. Next we want to define partial isometries. So here we have one observation. So you collect set of all unitaries in B of H such that U is unitary, then forms a multiplicative group in B of H. Okay. So next we discuss about partial isometries. Let V be a bounded linear operator from H1 into H2. Then we say that V is called a partial isometry if so V restricted to null space of V perp is an isometry. That means norm Vx equal to norm x for every x in null space of V perp. That means V is an isometry. So V restricted to null space of V perp is a map from null space of V perp into H2 is an isometry. So in this case, null space of V perp, so this is called the initial domain or initial space of V, and range of the operator is called the final space or final domain of V. So that means when you look at this map, V restricted to null space of V perp. So V restricted to null space of V perp. If you look at this from null space of V perp into onto range of V, so this is a bijective, is a bijection and isometry. So this is a unitary map between two different Hilbert spaces. Okay, so the meaning of partial isometry is nothing but restricted to a subspace, it is an isometry. So for that reason it is called a partial isometry. Okay, so let us see a few examples. So define P from R2 into R2 by P of xy is x comma 0 for every xy in R. We can consider it from C22 into C2. So then we can see that P is linear. Of course it is bounded because the domain space is finite dimensional space. So null space of P in this case is 0y, where y is coming from P of xy equal to 0 0, that means x should be 0, and range space of this is the x-axis. So we can say that this is range of P and this is null space of P. So null space of P perp is exactly range of P. So here we can easily show that P is also self-adjoint, and range of P is closed here. So P restricted to null space of P perp, that means when we restrict P to x-axis, it is of the form x comma 0, it sends to x comma 0 only. So that P restricted to null space of P perp is the identity map onto the corresponding space. On the remaining space it is 0. Hence since this is an isometry, we can say that this is a partial isometry. So therefore P is a partial isometry with the initial space null space of P perp and the final space, that is range of P, again equal to null space of P perp. Okay, so let us look at one more example. So let us take a complex number lambda with mod lambda equal to 1. Define V from L2 into L2 by V of x1, x2, x3 so on is mapped to 0 0 lambda x1, lambda x3, lambda x4 for every xn in L2. So the matrix of V with respect to the standard orthogonal basis L2, so this is nothing but zero zero lambda 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 so on. So here this is E1, E2, E3 so on. Now null space of V in this case is span of E1, E2, and null space of V perp is span of E3, E4, E5. Okay. Now V restricted to null space of V perp. Now it's a map from null space of V perp into range of V, but in this case so V star, the matrix of V star with respect to the same standard orthogonal basis 0 0 lambda bar lambda bar. So we can say that V restrict to null space of V perp it's a map from null space of V perp into range of V, but here we can show that it is also equal to the same space, null space of V perp. And so the corresponding matrix with respect to the standard orthogonal basis of this particular space, null space of V perp, that is span of E2, E3, span of E3, E4, E5, so on. So this is nothing but you will get lambda, 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 so on. Okay. So this is lambda times identity operator on this space. Hence this particular restriction is isometry. Hence we can say that original map is partial isometry. So therefore V is a but this is not an isometry, because if at all this is an isometry, it has to be 1 1, but here kernel of V is exactly span of E1 and E2, which is non-zero. So this is a partial isometry but not an isometry. Okay, now we can also show that we can ask what will happen if V is a partial isometry. Can we say that V star is also partial isometry? We have seen that whenever an operator is an isometry, its adjoint need not be an isometry. We have seen an example, that is the right shift operator on L2 is an isometry, but its adjoint, the left shift operator, is not an isometry. But surprisingly here we can show that easily, show that V in B of H1 H2 is an isometry is a partial isometry if and only if V star is also a partial. So find the relation between the initial and final spaces of V and V star. Okay, so we are going to use this concept of partial isometry at a later stage to analyze an operator in a better way. So that we'll be looking at a later stage. So let me quickly recall. We have discussed about isometries. Now using the properties of isometries, we have discussed about unitary maps or unitary operators, and after that we discussed partial isometries. In the next class we will be discussing about orthogonal projections which are connected with partial isometries again. So I'll stop here. Thank you very much.